In this section, we will be talking about rational functions. A rational function is defined as a function that is the ratio of two polynomials. So if p of x and q of x are polynomials, where q of x is not equal to 0, a function f defined as p of x over q of x is called a rational function. Our ultimate goal in this section is to learn how to graph a rational function. And the graph of a rational function has some very specific characteristics called, which we refer to as asymptotic behavior. So to understand this asymptotic behavior, we need to introduce some notation that we haven't really used before. So let's just take a look at this little chart here. When we say that x approaches c with a little plus subscript, we would interpret that as x approaching c from the right. So this means that so c represents a specific number, and this is saying that x is approaching c. X is getting closer and closer and closer to c, but it will never quite equal the value of c. And when we say from the right, that means that x is a value that's larger than c. So like c might be 2, and x might be 2.1. And as it gets closer to c, it might become 2.01, 2.001, 2.0001, right? It gets closer and closer and closer, but it's always bigger, and it never quite equals. As x approaches c minus, that means x approaches c from the left, right? So x is a value that's smaller than c, and it gets closer and closer and closer to c, but never quite equals it. And then x approaches infinity, x with the arrow and the infinity sign. This means that x increases without bound. It just gets bigger and bigger and bigger and bigger. And then the x arrow with a negative infinity, this simply means that x decreases without bound. It gets smaller and smaller and smaller without ever stopping. So the reason why this notation is important is because it helps us describe asymptotic behavior. Here's an example of a simple rational function. We have the graph of f of x is the f of x here is equal to x minus 1 over x minus 3. So this is a ratio of two first-degree polynomials, right? And over on the right side of the screen there, you see the graph of this polynomial, right? So we'll learn how to make these graphs later, but for now, we just want to look at the graph and examine some characteristics. You see the vertical dotted red line and the horizontal dotted red line. Those are not actually parts of the graph itself. The graph of the function is the solid blue lines there. But the dotted lines represent asymptotes. Okay, so what you see with the vertical dotted line is that the graph approaches that vertical line, but it never quite touches it, right? So we're seeing basically the function is approaching but never quite equaling a specific number, okay? And then the horizontal vertical line, the horizontal dotted line, that is the horizontal asymptote. Similar behavior exists there, right? The graph kind of gets closer and closer and closer, but does not touch or cross that horizontal line, right? So if we want to fill in the blanks over here, we could say as x goes to infinity, what happens to the function, right? Well, so as x gets bigger and bigger and bigger without bound, what happens to the function? Well, as x gets bigger without bound, as x gets bigger and bigger and bigger, what happens is the function approaches this horizontal red line, the horizontal asymptote, and that horizontal line passes through y equals 1, right? So as x goes to infinity, we say that f of x approaches 1. Okay? Similarly here, as x goes to negative infinity, similar thing, right? So over here we see that as x gets smaller and smaller and smaller without bound, right? The graph again approaches the horizontal dotted line. Again, we say that it approaches the number 1. Okay? But as x gets bigger without bound, what we see is that it approaches the horizontal asymptote from above, right? So we could specify that from above. And then over here, as x gets smaller and smaller without bound, the graph approaches the horizontal asymptote from below. So again, we could specify that, right? We could say from below. And then over here, what we see is that the vertical asymptote actually is a vertical line that passes right through x equals 3, right? So when it says as x approaches 3 plus, that's saying as x approaches 3 from the right? So as the graph of the function, as we move closer and closer and closer to the vertical asymptote, what happens to the graph? Well, we see it just increase, right? It keeps going up and up and up and up without bound, right? So we would write that as f of x approaches positive infinity, okay? And as x approaches the vertical asymptote from the left, what we see is that the graph just keeps going down and down and down and down. It keeps decreasing without bound, right? So as x approaches 3, the minus sign means from the left. The function approaches, we would say, negative infinity. Okay? So asymptotic behavior is a very key aspect of the graph of rational functions. And as you can see, when we are creating the graph, one important piece of that process, or one part of that process, is identifying any asymptotes that may exist. So now we're going to discuss the different types of asymptotes. We'll start by talking about vertical asymptotes and how we find those. Okay, so moving on here. So how to identify a vertical asymptote. Okay. Well, here's a definition of a vertical asymptote. The line x equals c is a vertical asymptote of the graph of a function f if f of x approaches infinity or negative infinity as x approaches c from either side, right? So that's the official definition, okay? So if we looked at this first diagram over here, right, as x approaches c from the right, the plus means from the right, f of x approaches infinity, right? So the vertical line there is the asymptote, so the asymptotic behavior would look something like that, okay? Over here, this is saying as x approaches c minus, that means from the left, f of x approaches infinity. It gets bigger without bound, right? So that would be something like this, right? As x approaches c from the right, f of x goes to negative infinity, right? It keeps decreasing without bound. That would be something like this. Putting a little arrow on there would be helpful just to specify that it keeps, the direction. And over here, as x approaches c from the left, f of x approaches negative infinity, right? So this would be something like this. Keeps going down without bound, okay? When you have just a rational function, how do you identify where the the vertical asymptote sits, right? Now, what you'll notice is that the function never crosses, it never touches or crosses the vertical asymptote, right? It gets very, very close, but it never quite touches or crosses. So that represents an x value where the function is undefined. And when you have a rational function, right, that involves the ratio of two polynomials, the place where it would be undefined would be where the denominator is 0. So the vertical asymptotes correspond to the x values that make the denominator 0. Okay? If we let f of x equal p of x over q of x, where p of x and q of x have no common factors other than 1, the vertical asymptotes, to locate the vertical asymptotes of f of x, determine the real numbers x where the denominator is 0, but the numerator is non-zero. To look at a couple of examples, scroll down here, identify the vertical asymptotes, if any. Okay, so for this one right here, we have a rational function where the numerator is a first-degree polynomial, the denominator is a second-degree polynomial, or also a quadratic. In this case, if we apply the rules we've learned earlier in the class for factoring quadratics, that quadratic in the denominator can actually be written in factored form as x minus 5 times x plus 1. Okay? And when it's written in that form, then it becomes quite clear that the values of x that make the denominator 0 are x equals 5 and x equals negative 1. So if you were to graph this polynomial, this rational function, you would see that there are two vertical asymptotes, a vertical asymptote passing through x equals 5 and a vertical asymptote passing through x equals negative 1. How about this one, right? With this one, the denominator is x squared plus 25. Any potential vertical asymptotes would correspond to where the denominator is 0. So if I set it equal to 0, can I solve? Well, I would get x squared equals negative 25. And to proceed farther would involve taking the square root of both sides, but that would involve taking the square root of a negative number, which is not a real number, right? It's an imaginary number. Vertical asymptotes can only correspond to real numbers. So that means that the graph of this particular rational function would not have any vertical asymptotes. Okay? Okay, let's now talk about horizontal asymptotes. Okay. First of all, a definition of a horizontal asymptote. Okay, the line y. Sorry, here we go. The line y equals d is a horizontal asymptote of the graph of a function f if f of x approaches d as x approaches infinity or negative infinity. So over here, we have the notation. As x approaches infinity, f of x approaches d, right? So as x gets bigger and bigger and bigger without bound, the function itself approaches the horizontal asymptote right here, right? So that's going to look like something like this, right? As x gets bigger and bigger, the function approaches the horizontal asymptote, but does not quite, doesn't equal it, right? Or a similar way that that could happen would be like this, right? So we could approach the horizontal asymptote either from above or from below. For here, we have as x approaches negative infinity, f of x approaches d, right? So this is saying that as x gets smaller and smaller and smaller without bound, the function approaches the horizontal asymptote. So that could look something like this. Like it could, as x goes to negative infinity, right, it could approach the horizontal asymptote from above, or it could look something like this, where it approaches from below. Notice that it actually is possible for a function to cross or intersect a horizontal asymptote, as we see here, right? So the asymptotic behavior essentially takes place when as x gets really big or really small, right? But for some other value of x, it may actually intersect or cross the horizontal asymptote. That is not the case for a vertical asymptote. It will never cross or intersect a vertical, but it can intersect or cross a horizontal. And we will, in a later example, we will look at how to identify the coordinates of the point where it crosses, where it may potentially cross a horizontal asymptote. But before we do that, let's look at a few examples where we want to identify the horizontal asymptotes. Okay, so here we have three rational functions, and we want to identify the horizontal asymptotes, if any. So a little trick that we could do is we could take the rational function and we could identify the largest power of x that exists anywhere in that function. And then we could divide every single term in the rational function by that largest power of x. For example, in problem 4 here, the largest power of x that we see anywhere is x squared. So what I'm going to do is divide every single term by x squared. So I get 3x over x squared divided by x squared over x squared minus 9 over x squared. Okay, so this is just, I just restated the rational function in a different way, right? So I've done exactly the same thing to every term, so nothing has changed as far as the value, it's expressed in a different form, okay? Now, on the numerator, 3x over x squared, I can cancel out a factor of x, so that becomes 3 over x. X squared over x squared is 1. 9 minus 9, and then we got 9 over x squared, right? And then we want to think about what happens as x either gets bigger without bound or gets smaller without bound, right? Either as x goes to infinity or to negative infinity, okay? That will tell us where the horizontal asymptote is. So let's just kind of focus on the numerator here, right? 3 over x. Well, as x goes to infinity, that means x is getting bigger and bigger and bigger and bigger. And as x gets bigger and bigger and bigger and bigger, 3 over x is getting smaller and smaller and smaller and smaller, right? So it's getting closer and closer and closer to 0. It will never quite get there, but it will get really, really close, right? So we would say that 3 over x approaches 0. I'm just going to express that this way. 9 over x squared, doing a similar thing, right? As x gets bigger and bigger and bigger and bigger, I'm taking 9 and dividing by a huge number. That's going to result in a very small number. And as x gets bigger, 9 over x squared will just get smaller, right? It will approach 0. Never quite get there, but it will approach 0, right? So the whole function will approach 0 over 1, right? Because 3 over x approaches 0, 9 over x squared approaches 0. All that's left is 1 in the denominator, which is, of course, equal to 0, right? So this is saying that as x gets bigger without bound, the function approaches 0. The whole function approaches 0. So the horizontal asymptote will be really just the x-axis, right? the horizontal line passing through y equals 0. Okay. I can do a similar approach for these other two, right? For this one, again, the largest power of x is x squared, so let's divide everything by x squared. F of x is equal to 3x squared over x squared over x squared over x squared minus 9 over x squared. Okay, this is equal to 3. On top, the x squared and the x squared, the factors of x squared cancel, right? So we've just got 3 on top. X squared over x squared is 1. So whole thing simplifies down to that. And then think about what happens as x goes to infinity. As x goes to infinity, 9 over x squared will approach 0. It will get closer and closer and closer to 0, right? So this whole thing will approach 3 over 1 or just 3, right? So as x goes to infinity, the function approaches 3. So the horizontal asymptote will be a horizontal line passing through y equals 3. Finally, let's do this one. Here, the largest power of x is x cubed. So I'm going to divide everything by x cubed. So 3x cubed over x cubed divided by x squared over x cubed minus 9 over x cubed. Okay. What do we got here? So on top, I just have 3. X squared over x cubed, that simplifies down to 1 over x. And then 9 over x cubed, right? So as x goes to infinity, 1 over x is going to approach 0. 9 over x cubed is going to approach 0. So this whole thing is going to approach 3 over 0, which is undefined. Okay. So that means that this function has no horizontal asymptote. Okay. Now, so this method will always work. Just divide every term by the highest power of x, right, and kind of analyze it. However, if we look at these 3 results, we can actually kind of boil this down to 3 helpful rules. And basically, the horizontal asymptote will always depend on the degree of the numerator and the degree of the denominator. For problem 4, we have a first-degree polynomial divided by a second-degree polynomial, right? So that means that the numerator is of a smaller degree than the denominator. And the result of that is that the x-axis was the horizontal asymptote. That will always be the case for any rational function where the numerator is of a lesser or smaller degree than the denominator. The x-axis will be the horizontal asymptote. Over here, the numerator is a second-degree polynomial, and the denominator is also a second-degree polynomial. In other words, the numerator and the denominator have the same degree. And the horizontal asymptote was found by taking the ratio of the leading coefficients. The numerator has a leading coefficient of 3. The denominator has a leading coefficient of 1. 3 over 1 equals 3. So the horizontal line passing through y equals 3 is the horizontal asymptote. With this one, the numerator is a third-degree polynomial. The denominator is a second-degree polynomial, right? So the numerator is of a higher degree than the denominator, and there is no horizontal asymptote. And that will always be the case as well. Anytime the numerator is of a higher degree than the denominator, the function will not have a horizontal asymptote. Okay? All of that can be boiled down to these 3 rules right here. Let f be a rational function defined by f of x equals a polynomial of degree n in the numerator and a polynomial of degree m in the denominator, where n is the degree of the numerator, m is the degree of the denominator. If n is greater than m, f has no horizontal asymptote. If n is less than m, then the line y equals 0, or the x-axis is the horizontal asymptote. If n equals m, then y equals a sub n over b sub m is the horizontal asymptote, right? The ratio of the leading coefficients. So that is how we find horizontal asymptotes of a rational function. Now, I mentioned earlier that it is not possible for the graph of a rational function to cross a vertical asymptote, but it is possible for the graph to cross a horizontal asymptote. And when you are graphing a rational function, that is an important thing also to check, to see if the graph intersects or crosses the horizontal asymptote at some point, and if it does, what are the coordinates of that point? So let's explore that with this function right here. F of x equals 2x squared minus 4 over x squared minus 3x minus 4, right? So we have a rational function, and the numerator and the denominator are both second degree polynomial functions. And I'll go back to the rules we just looked at. When the degree of the numerator is the same as the degree of the denominator, the horizontal asymptote will be a horizontal line passing through a number dictated by the ratio of the leading coefficients, right? The numerator has a leading coefficient of 2. The denominator has a leading coefficient of 1, right? So the horizontal asymptote will be a horizontal line passing through y equals 2. In order to determine if the function crosses the horizontal asymptote, I would want to take the function and set it equal to 2, right? Basically replace y with 2 and then see if I can solve for x. Okay, so if I do that, I get 2 equals 2x squared minus 4 over x squared minus 3x minus 4. And then I'll multiply both sides by the denominator, right? So I get, let's do over here, 2 times x squared minus 3x minus 4 equals 2x squared minus 4. If I distribute the 2 on the left here, I get 2x squared minus 6x minus 8 equals 2x squared minus 4. Okay. If I subtract 2x squared from both sides, then the 2x squared terms just cancel out, right? So then I'm left with negative 6x minus 8 equals negative 4. And then if I add 8 to both sides, I get negative 6x equals 4. And then divide both sides by negative 6. I end up with x equals negative 4/6, or that reduces down to negative 2/3, right? So when y equals 2, the value of x equals negative 2/3. So yes, the graph does cross the horizontal asymptote at the point negative 2/3, comma 2. Okay. Okay. There is one other kind of asymptote that we have not yet talked about. We've covered horizontal and vertical asymptotes, but it is also possible for a function to have a asymptote that is slanted or angled, right? That's neither horizontal nor vertical. A rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. And if so since a slant asymptote is neither horizontal nor vertical, then the slant asymptote can be described using an equation, right? Like an equation in slope-intercept form. It will not be equal to like a specific number, like it is for a horizontal or vertical. To find an equation of a slant asymptote, what we can do is we can divide the numerator of the function by the denominator, and the quotient will be linear, and the slant asymptote will be of the form y equals the quotient. Okay. Let's take a look at an example, right? Here's a rational function we looked at earlier. This one, the numerator is 3rd degree, the denominator is 2nd degree, right? So the denominator is 1 degree less than the numerator, so that means this will have a slant asymptote. And let's divide. This one does not, synthetic division will not work here because the denominator is x squared minus 9. It's not linear. So we'll have to use long division. So we'll set it up like this. X squared minus 9. Okay, under here I've got 3x cubed. Oops, I should have given myself more room, but we'll make it work. So put a 3x up here, because when I multiply, I want to end up with a 3x cubed minus 27x. And what I like to do is, so you're subtracting, right? But subtracting means adding the opposite, right? So that becomes a 0, and I just kind of bring down the 27x. So the 27x here is the remainder, okay? And so but when we're trying to find the equation of the slant asymptote, we actually just ignore the remainder, and the quotient just without the remainder represents the equation of the slant asymptote. So the slant asymptote will be dictated by the equation y equals 3x. Okay, if you graph that, it would be an angled straight line corresponding to where the slant asymptote is. Okay, so we've touched on a lot of characteristics of rational functions, right? How to identify horizontal, vertical, slant asymptotes, and how to identify where a function potentially may cross a horizontal asymptote. So our next step now is to actually go through the process of graphing a rational function, right? So here's a good set of guidelines when graphing a rational function. F of x represents a rational function, right? P of x over Q of x, where P of x and Q of x are polynomials with no common factors, right? So pretty much for graphing any function, it's always a good idea to identify any intercepts, x and y intercepts, right? We've had a lot of practice on how to do that. Set x equal to 0 and solve for y, and then vice versa, set y equal to 0 and solve for x, right? But then specific to rational functions, identify any asymptotes, determine if the function has vertical asymptotes and graph them as dotted lines, determine if the function has a horizontal asymptote or a slant asymptote and graph the asymptote as a dashed line, right? Determine if the function crosses the horizontal or the slant asymptote, right? Other things that can be helpful, right? Doing a symmetry test. checking to see if the function is an even or an odd function, to see if it exhibits symmetry relative to the y-axis or the origin. That's a fairly simple thing to do, and if a function does exhibit symmetry, then it can make the graphing process simpler, right? Because there's less of the graph you have to figure out because of the symmetry. And then after identifying any asymptotes, intercepts, or symmetry, you may need to plot a few additional points just to fill in some other details of the graph. Good rule of thumb here is to plot at least one point on the intervals defined by the x-intercepts, the vertical asymptotes, and points where the function crosses a horizontal or a slant asymptote. So let's go through a few examples where we actually graph. Okay, here is our first example of graphing a rational function. We have the function f of x equals x squared minus x minus 6 over x squared minus 5x minus 6. So let's start by identifying any intercepts, and we'll start with the x-intercepts, right? So what I have here is, in order to find the x-intercepts, we have to set y equal to 0. So I have x squared minus x minus 6 over x squared minus 5x minus 6, and I set this equal to 0. Now I could multiply both sides by the denominator, which gives me x squared minus x minus 6 equals 0, right? The denominator really just essentially goes away. So in other words, when we're finding the x-intercepts, right, the only way for the function to be 0 is if the numerator is 0, right? So this numerator is a quadratic, and that quadratic can actually factor as x minus 3 times x plus 2. And so the values that make the numerator 0 here are x equals 3 and x equals negative 2. So the x-intercepts are, just say x-intercepts here, the points 3, 0 and the point negative 2, 0. Okay? Y-intercept is easy because we just evaluate f of 0, right? And if you plug in x equals 0, then everything with an x goes away, so I'm just left with negative 6 over negative 6, which equals 1. So the y-intercept is the point 0, 1. Okay, and I could actually even start plotting those over here if I want to, right? So negative, let's see, 1, 2, 4, 6, 8. So these are actually increments of 2. So negative 2, 0 is the point right there. 3, 0 is right there. Okay. And then 0, 1 is right there. Okay. All right, so next step would be to identify any asymptotes. Okay. Start with vertical. Vertical asymptotes always correspond to where the denominator is equal to 0. So I'm just going to say VA as an abbreviation for vertical asymptotes. To find these, I set the denominator equal to 0, x squared minus 5x minus 6 equals 0. And this can factor as x minus 6 times x plus 1. And that's equal to 0. Okay. And so the values of x that make this 0 are x equals 6 and x equals -1. Okay, those are the vertical asymptotes, and I can plot those over here. -1 is about here. Just put that in as a dashed line. Okay. Just to indicate where it is. And x equals 6, it's right here. Again, put that in as a dashed line. And then horizontal asymptotes, we'll do that as well. Okay. So we've got, to find the horizontal asymptotes, we look at the degree of the numerator and the denominator. And they're both second degree polynomials, so the degree is the same. And so in that case, we take the ratio of the leading coefficients. And so we've got y equals 1 over 1, which equals 1, right? So the horizontal asymptote is actually a horizontal line passing through y equals 1, which will be right about here. Okay. And then just kind of coincidentally, in this case, we see that the y-intercept also happens to be a point where the line crosses the horizontal asymptote. Okay. And so we've got, so the two vertical asymptotes kind of tell us that the graph will be divided into 3 separate regions. And remember that the function will never cross a vertical asymptote, right? So this region and this region, we can kind of get a sense of what the graph is going to look like, right? It's going to pass through here, and it's going to come up and approach the horizontal asymptote, and then come down and approach the vertical asymptote, right? Here, it's going to come up here, approach that vertical asymptote, go over here, go through that point, come down like that, right? We don't really have a great sense of what's going to happen over in this region, right? So for that, it would be helpful to maybe plot an additional point, right, or two. Keep in mind that this vertical asymptote here passes through x equals 6, right? So any points that I choose should be a point to the right of that, right? So like maybe plug in x equals 7, right? So evaluate f of 7, right, which equals 7 squared minus 7 minus 6 over 7 squared minus 5 times 7 minus 6, right? Simplify that down. That's equal to 49 minus 7 minus 6 divided by 49 minus 35 minus 6. And if you work that out and simplify, it's actually going to plug that into your calculator. It's going to be 4.5. So we've got the 0.7 comma 4.5. Okay. Let's see, 4.5 is about here, right? And so that tells me basically that this portion of the graph is going to be sitting above this horizontal asymptote. So we'd be looking at something like this, coming down, something like this, right? And it's going to look about like that. And, you know, if there's ever any doubt, you can always plot additional points, right, to fill in more details. Just kind of keep in mind that the vertical asymptotes separate the graph into different regions, right, where the graphs don't connect, right? So you'd want to kind of fill in the details in each of those different subregions. All right. Let's take a look at another one. Okay. Here's our next example. F of x equals 2x squared over x squared minus 4. So let's kind of go through the same process we did with the last example, right? So we've got, let's find the x-intercept first. Just say x-intercept. Okay. This is always going to correspond to where the numerator is equal to 0, right? So we could say 2x squared equals 0. And if you solve that for x, you'll find that x equals 0, right? So when x equals 0, y equals 0, so the point 0, 0 is the x-intercept. It's also a y-intercept. It's the origin, right? Let's plot that right now. And let's see if there's any other y-intercepts besides the one that we just found. Y-intercept is found by evaluating f of 0, which equals 0, right? So 0, 0 is also the only y-intercept. Let's find any vertical asymptotes. Okay. Once again, the vertical asymptotes correspond to where the denominator is equal to 0. So x squared minus 4 equals 0. Or if we solve that, we've got x squared equals 4. Take the square root of both sides. X equals plus or minus 2. So we have two vertical asymptotes corresponding to x equals 2 and x equals negative 2. Right? Those will be right here. So negative 2 right here, and positive 2 right here. Okay. And horizontal asymptotes. And once again, we look at the degree of the numerator and the denominator, and they're both the same degree. So in that case, the horizontal asymptote is found by taking the ratio of the leading coefficients, which will be 2 over 1, which equals 2, right? So the horizontal asymptote is a horizontal line passing through y equals 2, like this, okay? And with this one, let's try doing a symmetry test, right? So if we do f of negative x, we get 2 times negative x squared divided by negative x squared minus 4. When you square a negative, you always get a positive, so this is equal to 2x squared over x squared minus 4, which equals f of x, right? So when we evaluate f of negative x, we just get the function right back. That means it's an even function and it will be symmetric to the y-axis. So that is helpful information, because if I can figure out half of the graph, then the other half will just be a reflection of that, right? So with that in mind, let's plot a couple of additional points, okay? Go up here, do a little XY chart here. Points to choose. Let's kind of focus on the right half of the graph, knowing the left half will be a reflection, right? Let's choose an x value to the left and to the right of this particular vertical asymptote, right? This is a vertical asymptote passing through x equals 2. So let's choose x equals 1, which is to the left of that, and x equals 3, which is to the right of that. Both of these x values I'll want to plug into this function, right? I want to evaluate f of 1, and if you do that, you kind of work that out on your calculator, you would get negative 2/3, right? So negative 2/3 right there. Similarly, if you evaluate f of 3, you would get you get 3.6. Okay, so that's what that is. Okay, so two other points, right? When x equals 1, y equals negative 2/3. That's about there. When x equals 3, y equals 3.6. 1, 2, 3.6 is about there. So this is going to tell me that the graph over here is going to look something like that. And over here, going to look something like that, right? And then over here, it's just going to be a reflection, right, because of the symmetry. So that's going to come down like that. And this is going to look something like that, right? So that's what that graph is going to look like. All right, and we'll just do one more example. We'll be done with this section. This one is one that involves a slant asymptote. Okay. F of x equals 2x squared minus 8x plus 8 over x minus 3. Let's start that the way we did with the previous two by finding the intercepts first. X intercept will correspond to where the numerator is equal to 0. So that gives me 2x squared minus 8x plus 8 equals 0. I can divide every term by 2, basically pull out a factor of 2, which gives me x squared minus 4x plus 4 equals 0. And this can actually be written in factored form as x minus 2 squared. X minus 2 times x minus 2. So x equals 2 is where that's equal to 0, or the point 2, 0. Okay? 2, let's see here. So these are going 2, 4, 6, 8. So yeah, the way this is scaled, 2, 0, 3, 6, 9, 12. These are actually increments of 3, right? So 2, 0 is going to be right about there. Okay. Y-intercept, of course, we just evaluate f of 0, which is going to equal 8 over negative 3, right, or negative 8/3. So the y-intercept is the point 0, negative 8/3. Okay. Which is going to be right about almost negative 3, but not quite. So about there. Okay. And then we'll do our asymptotes, right? So vertical asymptote, this always corresponds to where the denominator is equal to 0. So this is an easy one, right? X minus 3 equals 0, so x equals 3 is the one vertical asymptote, and that's going to be the vertical line passing through this. Like so. Okay. All right, and then for horizontal asymptotes, what we do is we look at the degree of the numerator and the denominator, and we see that the numerator is of a higher degree than the denominator, and when that's the case, there are not any horizontal asymptotes, so there are none. But there is a slant asymptote, and that's because the numerator is exactly 1 degree more than the denominator, right? Numerator is second degree, denominator is first degree. To find the equation of the slant asymptote, we divide, ignore the remainder, and just use the quotient as the equation for the slant asymptote. And in this case, we can actually do synthetic division because the denominator is a linear term. So the number being subtracted from x is 3. My coefficients are 2 for the x squared term, negative 8 for the x term, 8 for the constant term. Right, bring down the 2. 2 times 3 is 6. Add to get negative 2. Negative 2 times 3 is negative 6. Add to get 2, right? So this is the coefficient of the x term, constant, and that's the remainder. But we ignore the remainder, and so the quotient without the remainder is just 2x minus 2. And that is the equation describing the slant asymptote, right, in slope-intercept form. So it's going to, if I were to graph that, right, it's going to intersect the y-axis at about 0, -2, which is right about here. Slope is up 2 over 1, right, about here, something like that. So, this is not perfect, but the slant asymptote is going to look something like that, okay? And then we graph, right? So I've already got 2 points that are kind of in this region right here, so that kind of tells me that this portion of the graph is going to look something like this, right? And again, you can always plot more points if you need more detail. But then, we might just plot some additional points to fill in details, okay? So like, for example, if I plot -3, plug that into the function and solve, I'm going to get -8.3. Okay, that's going to be a point down in this area, right? If I plug in -1, I'm going to get -4.5. Okay, that's going to be a point down in this area as well. If I plug in x equals 1, I'm going to get -1. That's going to be down in this area as well. If I plug in x equals 4, and this is a value of x on the other side of the vertical asymptote, I'm going to get y equals 8. Okay, 4 is over here, 3, 6, 9. That's going to be right about here. Okay, maybe x equals 5 as well. Okay, 3, 5. That gives me 9, which is up about here. So that's going to tell me that up here, the graph is going to look something like this, basically. Okay, so that's how this graph is going to look like. So that's kind of the general procedure for graphing a rational function, right? Identify intercepts, asymptotes, kind of put the asymptotes in there as dotted lines, and then if needed, plot additional points as necessary. And that wraps up this section. Thank you for watching.